So now let omega contained in Rn be an open set of class C1. So then what do you have? This is omega, it has bounded boundary, and for any point on the boundary you have this is q plus, this is q0, and this whole cube is called q, and you have a map which takes you Tj, which goes to this, the boundary goes to this Tj, and Tj and Tj inverse are all C1 maps. Okay, and these are, so you can cover, so Uj Tj associated cover of d omega. Let us call that as gamma. And then psi j, so j equals 1 to k, associated partition of unity. So if u belongs to h1 of omega, then psi j of u restricted to uj intersection omega composed with tj and then extended by 0 outside the cube will belong to h1 of Rn plus. And so we can define its trace, so gamma naught of can be defined, so trace on Rn minus 1 can be defined, and go back to gamma intersection uj by tj inverse. So this defines the trace on uj intersection gamma, and again use the partition of unity and piece together gamma trace on tj, gamma intersection uj, j equals 1 to k to get trace on gamma. Okay, and we can have range of gamma naught, so we will get in fact gamma naught from h1 of omega to L2 of gamma. Okay, and then range of gamma naught will be h half of gamma, and kernel of gamma naught will be h10 of omega. Okay, so more generally we have the following theorem. So theorem, trace theorem. Omega in Rn, bounded open set of class Cm plus 1. Then there exist maps gamma naught, gamma 1 up to gamma m minus 1 from hm of omega into L2 of gamma, gamma equals d omega, such that 1. If V belongs to Hm of omega sufficiently smooth, then gamma naught V equals V restricted to gamma. Gamma 1 of V is dV by d nu restricted to gamma, and then etc. Gamma m minus 1 V equals d m minus 1 by d nu m minus 1 V restricted to gamma. So these are all the various higher order normal derivatives, where nu is the unit outward normal to gamma. So you have the boundary here, and then at each point you have a tangent, and then you have nu, which is the unit normal vector, which is there. Okay. 2. Range of gamma naught gamma m minus 1 is pi j equals 0 to m minus 1 h m minus j minus half of gamma. And then 3, kernel of gamma naught gamma m minus 1 equals hm0 of omega. Okay, so this is the trace here. So if omega equals b0r, then nu is nothing but x over r, that is the direction radius vector itself is the normal for mod x equal to r. Okay, this is the unit normal. Okay, and if you have Rn plus, as I said, omega equals Rn plus, then nu equals minus En. Okay, so we have, these are the examples of this. So now we have theorem. This is Green's theorem. Omega in Rn, bounded open set of class C1. Gamma equals d omega. Okay. uv in h1 of omega. Then for 1 less than equal to I less than equal to n, we have integral on omega u dv by dxi dx equals minus integral on omega u du by dxi v dx plus integral on gamma naught u gamma naught v into nu I dx. So the ith component is the thing, where nu is the nu 1 nu n unit outer normal on gamma. Okay. In particular, if one of them is in h10 of omega, then you have integral omega u dv by dxi dx equals minus integral u du by dxi v over omega dx. Okay, and this is so proof. So we know because of Friedrich's theorem and so on, you have that C infinity of omega bar is dense in h1 of omega. In fact, d of Rn itself will be dense in h1 of omega, and so C infinity omega bar is dense in this. So if un converges to u, Vn converges to V in h1 of omega, un Vn in C infinity omega bar intersection h1 of omega, then you have, by the classical Green's theorem, integral of omega um dvm by dxi un dvn by dxi dx equals minus integral omega dun by dxi vn dx plus integral on the boundary of un vn nu I. This is the classical Green's theorem. Now you let n tend to infinity, and you have, this is un converges to gamma naught u, and Vn converges to gamma naught. So, and you have everything else. Okay. So in future we will write, in future we write V instead of gamma naught V on d omega equals gamma, dV by d nu instead of gamma 1 V on d omega, etc., whenever defined. Okay, so because we know what it is, and okay. So now let us take some simple consequences of this Green's theorem, which will be useful in the next chapter. So we set u identically equal to 1 and v equals vi in h1 of omega, omega bounded open set. So you get integral on omega dvi by dxi dx equals, that is u, du by dxi is 0, and therefore that will not be there. So and then integral on gamma u, that is this thing, and vi nu I d sigma. Okay. So should write d sigma, which is the surface element for the integration on the surface. Now v equals v1 to vn in h1 omega power n, and then you write this for each I and sum over I, you get integral on omega sigma dvi by dxi dx I equals 1 to n equals integral on gamma sigma I equals 1 to n vi nu I d sigma, and that is exactly the Gauss, that is divergence of v integral on omega equals integral on gamma v dot nu, and that is d sigma, and this is the Gauss divergence theorem. Okay, so now let u is be in h2 of omega, and so you write integral on omega du by dxi dv by dxi dx. So that will be equal to minus integral d2u by dxi square v dx, and then plus integral on gamma du by dxi v nu I d sigma. Now if you sum over I, you will get integral on omega grad u dot grad v dx equals minus integral on omega Laplacian of u times v dx plus integral sigma du by dxi nu I is precisely du by d nu times v d sigma. Okay. Now if u and v are both in h2 of omega, then we can write the same thing with v instead of u. Then if you subtract, then you will get integral u delta v minus v delta u dx is equal to integral on gamma u dv by d nu minus v du by d nu d sigma. Okay, so all these are various applications. We will use them. So we come to the end of this chapter, but before winding up, we will do some exercises in the next session.